Hi again, this is Nikos Petrelis, and in this third video we will try to see the use of the timer counters, and the first use of these peripherals will be to replace the dummy delay that we were creating in our blinking LEDs examples in the previous two videos with a timer counter that we will check if it has been overflown in order to see if the delay has been measured correctly before switching on or off the LEDs. So let's first create a new project to remember the whole process again. New microvision project, let's keep it within the microcontrollers, and I will give the name, as my notes say, test TIM2 overflow. Let's make also make a new directory with this name. Okay. It is an STM32 microelectronics 407 VGT. Select it. Okay. I configure that concerns the board STM32F for discovery. Then from the CMSIS, as we did in the first video, select the core support. In the device, the startup, and under Cube Framework, we select Classic Framework. In our next videos, we will see the STM32 CubeMX framework. So after this here, we have to resolve initially the issues that arise in the validation output frame. It has been clear, and we will see what had been selected already in our previous projects too. But now we have to also include the timer peripherals. So I check this one here. Okay. So I selected TIM, and now I think we have not changed what we had here. No, we have to place again, since it is a new project, use HAL _HAL driver. Use HAL driver, and in the paths we select our current path, this one here that is suggested. Okay, this is needed to find all the include paths that will be placed here. In the linker, in the debugger, let's say, again, we have to select the ST-Link debugger. My board is already connected, but as we found out in the first video, we have to change the JTAG interface. Okay, it has been found now, and it's okay at this point. So let's place our code. We add a C source file called code main, and I'm gonna copy paste my code here. I will describe it briefly to you before I execute it. Okay, here it is. So let's see how we use the TIM2. This is the number 2 timer counter. First of all, I have to remind you that timer counters are peripherals that can count either events. By events we mean modifications, changes in the value of a pin. For example, when a pin changes from 0 to 1, it's a single event. If it repeats this modification, this change from 0 to 1 multiple times, the counter can count how many times this pin changed from 0 to 1. This is the counter mode. If we use a timer as a timer mode, in the timer mode, then we do not count the events on an external pin, but we use an internal oscillator, and we count pulses. What we can do with the timer, the first thing is, for example, that the timer counter will count pulses on my internal clock, but when it reaches the top value, the higher value that it can get according to its resolution, then it will return to 0 if it is an up counter, and we will get an overflow. So one event that we are likely to be interested in is to detect if an overflow has occurred. Let's see how we can exploit this operation of the timer counters in our project. Again, I remind you that our project simply blinks the LED, but now instead of having, as we had in our previous projects, a for loop here, which inserted a dummy delay, what we are doing now is that we will be checking if an overflow occurred in our TIM2 timer counter, and if it occurred, then we know that the delay has finished and we can move to the next operation, which will be to either turn on or turn off the LEDs. But let's see during the initialization what has to be done. I have already explained that this command here enables the clocks to GPIO-D and GPIO-A, although in this project we actually will not need a switch, so GPIO-A may not be needed at all. But we will also have to give internal clock to the TIM2 timer counter. And its enable bit that is not in this register where the GPIOs had to be enabled, but in another enable register with this name here, APB1 enable register. So with this operation, or the previous value of the register with this mask, and this mask has simply a single one at the place where the TIM2 enable bit is, just enables this peripheral, the TIM2 timer counter. We again, as we did in our previous project, set the mode of our pins 12 up to 15 of GPIO-D to outputs because the LEDs are connected there in our STM32 discovery board. And now, the configuration of the timer 2 is performed in these highlighted operations. And let's see what some of these registers, the registers ARR, EGR, CNT, PSC, SR, CR1, all belong to the TIM2 set of configuration registers. This structure here shows to the address of each one of these registers. And in order to avoid placing directly hexadecimal addresses, we use this notation in order to access in a more readable way the position of the configuration registers we need. So ARR, first of all, is the register that defines the top value that the timer will reach before it returns to the 0 value. So this register, as you can expect, is a 32-bit register since we have 8 hexadecimal digits. So its resolution is 32 bits, but we set the top value, the overflow value, to much lower than the case where all of these digits were F. So when the timer will reach the value 0, 1, F, 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 F in hexadecimal, we will get an overflow. Other important configuration registers are the counter, which sets the initial value of the counter. It will start from 0. The prescaler register determines if we like to have a prescaler. A brief description of the prescaler is that we can make the timer change its value slower in the timer mode. For example, we can set it to avoid changing its value in every single pulse at its input. But we can say, for example, that it has to change its value to update, to increase by 1, let's say, its output value by 1 in every 8 input pulses. In this case, we would say that we will have a prescaler 1 to 8. If we like to say that we desire to have the timer changing its output value in every 256 values, 56 input pulses, then we would say that we will have used a prescaler 1 to 256. You can read, of course, the theory behind the timer counters in all the manuals of the microcontrollers. The status register contains some useful information that we can check. For example, it contains the bit that shows if an overflow has occurred, but we initialize it to 0 in order to clear all previous conditions, in order to avoid inheriting a condition from a previous run, for example. And the CR1 control register 1, there are multiple control registers in each timer counter, has to be set with these configuration bits. One of its bits, for example, the CE enable simply enables the counter in order to proceed its counting in every pulse. If we like to pause the counting, we can zero this bit here. You can find out from the datasheet what the other bits are used here. But all of this initialization is adequate for our case. So the infinite while loop starts here. And as we had in our previous projects, it starts by turning on all the LEDs. We explained this notation here in a previous video. But now, at the delay, we use the temporary value TMP, which is set initially to 0, but in each iteration of this while loop here, this TMP value is loaded with the value of the status register and the mask with the overflow bit. This mask here has a single 1, all the other bits are 0, at the place that corresponds to the overflow indication of the timer 2. So, if this end operation here returns a non-zero value, this means that we had an overflow. So we can leave the while loop in this case, clear the status register, the delay has been measured, and we proceed to the next operation, which is the one that turns off the LEDs. The second delay is exactly the same as the first one. So we simply build the project, you can see below the messages. Oh, we get some errors here. Well, from the messages shown earlier, all of them concerned that some definition about DMA was missing. DMA is a peripheral for direct memory access. We had not clicked it. So let's click this from the Manage Runtime Environment. Let's also click this DMA checkbox here and repeat the building the project. This will actually insert all the header files where declarations about DMA exist. So we hope that the missing declarations that were the errors shown earlier will disappear now. So after this one, we build again the project. We do not see all this large list of errors generated earlier. So we hope that this solves our problem. Okay, 0 errors. So this problem was solved by also including DMA support in our project, because this handler here exists in some header files that belong to the DMA peripheral. So after successfully building the project, let's download this to the flash memory of the development board, and let's start the session. So I directly run, and as you will see shortly, my LEDs are blinking. As you can see, the LEDs are blinking, but now the delay is comes from the check of the overflow of the TIM2 timer counter. But let's see what we could do if we would like to have the LED blinking more fast. What we can change in our code to establish a higher speed in the blinking. So we return to our code and stop the debugging. And we can see that the delay is determined by either the use of a prescaler. So here no prescaler is used, but if we would like to make it slower, we could use a prescaler. This is left as an exercise to you to find which values could be set here to the prescaler value in order to slow at a half speed or at a quarter of the speed that was shown earlier. But there's also another trick we can do. We can reduce this upper value where that is reached by the counter in order to determine when the overflow occurs. So let's make it half, let's say. This can be done by 0 in this one and setting this one to 7 FFF. So you will see that this value is about the quarter of the previous value. So we will have a much faster blinking, 4 times faster actually than previously. So let's build the project. Okay, built without errors, flash download, completed, start debug session. Run. And the blinking is quite faster, so you can see it right now. So here are the LEDs that, as you can see now, they blink quite faster than previously. Thank you for watching. See you in the next video.